So yesterday we introduced this notion of real mixed Hodge structure, which consists of real vector space, a filtration, increasing filtration, a decreasing filtration. So this is on R and this is on HC. And then such that grade F bar Q grade FP grade Wn is 0 if P plus Q is not equal to N. So this is what was, and then we said various things. So one thing I just wanted to remark that I may have given some slightly wrong impression, and so we said there is a HPQF, which was, I gave the definition, I don't want to write it again, or it's in the notes, but okay, maybe I'll write it. Wn intersection FP intersection Wn intersection FQ bar plus sigma I greater than equal to 0 Wn minus I intersection F Q plus I minus 1 bar. Right? And so from this formula it's clear that if I take the bar of this, then this is Wn intersection Fp bar intersection Wn intersection Fq, right? Because Fq bar is Fq bar greater than 0 Wn minus I intersection Fq plus I minus 1. Okay, and which, if you look at the definition, this is equal to the definition of HQP F bar. Okay, so that identity I did not point out yesterday. It's worth noting because it means that various things you only need to check for F and automatically they will follow for F bar. Okay. But the point is that unlike the case of pure Hodge, where this is true without the bar, without changing the subscript, here the subscript changes. So it is HPQ bar is not HPQ F bar, but F bar.
F bar is not F.
Is not F. I mean, this term is in general not equal to the same thing with the bar. And that's the point.
And yesterday's terminology, I would say a mixed Hodge structure is trivial if F bar equal to F.
Well, it's pure. It's not pure. Okay, pure is unmixed. Okay. So, right. And then what I had started towards the end is to try to associate MHS to cohomology. Right? And to do this, I started by introducing for X is a smooth quasi-projective variety. Well, I am always in quasi-projective case. But probably, as various people have pointed out, many of these things will work without even assuming that it's quasi-projective. Sitting inside X, where this is complete, so it's projective. X bar, smooth projective. And X bar minus X is a divisor of normal crossings. Is a divisor with simple normal crossings. Which means that for every X in X bar, there is some neighborhood N such that if if di intersection n is non-empty, then it is given by a function fi. Its di intersection n is vanishing of some fi. So these are the irreducible components, I should say. So, and these are part of a regular system of parameters. So let's say where f1, f2, fk, if these are the ones which occur, then they can be extended to fk plus 1, etc. Fn is, so these are the ones associated to di's, and plus some more are a regular system of parameters at x in n, x in x bar. Okay, so that's a simple normal crossing divisor. And then we said that associated to this, there is a omega 1 x bar. Now I'll adopt my notes, which I'm now writing today. Is hopefully it will be, all these changes will be correctly made. I will use this log notation rather than Deline's notation. If you look at Deline, the reference which I have given in the notes, Deline uses this symbol. So omega 1 x log is locally, again in n, the span of OX span of df1 by f1 dfk by fk dfk plus 1 dn dfn. Okay. And because of the definition was given of the sheaf in a global fashion, so it's a globally defined sheaf which is locally free of rank n, and then you can take its exterior algebra. So this is defined to be omega dot. Yeah, bar. Yeah, Deline actually uses x for this and x star for the actual x which we are interested in. I found that a bit strange because we are interested in x ultimately, not x star.
It's like C and C star.
In fact, it is, yes. Locally. Okay. So this is the, and then the point is that this is some local checking to check that this is closed under differentiation. Right? So it's a differential graded algebra or whatever you call it. Okay. And then essentially so one thing I mean I didn't ask, so I'm not sure should I say anything about what is hypercohomology or not.
Say it in 2 sentences.
Okay, so let me quickly say what is so there are two things. So hypercohomology, yeah. So suppose I have a complex of sheaves. Okay, I'm always, since they are bounded, may as well take it to be bounded, and I will, for simplicity, assume that the indexing starts at 0, which is not necessary. Then what you can do is that you can patch together and make a kind of simultaneous resolution by flask sheaves or injective sheaves and so on of this kind. Okay, so on and so on. You can make a double complex, and then one can take the total complex of this double complex and take its cohomology, and that's one can show that it is independent of the choice of simultaneous resolutions. So simultaneous resolution, by the way, it means that each of these complexes you can split into, so for example, bi goes to, sorry, zi goes to fi goes to bi plus 1 and so on, right? So you can split it into short exact sequences. You resolve each of these and then the sum of those will give you a resolution of this if it is injective and so on, and you can lift everything and make a double complex. Then put all those together, you get a...
You have to start one step behind. First resolve B, Z, H. Then...
Oh yeah, I've forgotten. You have to also do this, the HIs, you're right. So you have to... Okay, so you have to start with somewhere. That's why the finiteness is important. You start somewhere, then you resolve this, and then you resolve the next one, then you put it together to get the resolution and so on. Okay, so I mean, some homological algebra which was done at some point by Eilenberg and somebody, Karta. Okay, Karta-Eilenberg resolution. You can look it up.
So write the word horseshoe.
Sorry?
Horseshoe lemma.
That's what it's called?
Well, that's what goes into all the implementation. That is TFR Sanskrit calls it horseshoe.
Okay. Okay, so these are some magic words which on Google will get you whatever you need to know about this. Okay, and then after taking the total complex of these complexes, you will get what is called the hypercohomology of F, and then one has to of course do the usual homological algebra and prove that it is independent of this. Okay. So the reason I got into thinking about how to do this, so in the analytic topology, you have one natural resolution here, okay, which is by real C infinity differential forms, and that's a fine sheaf. So you don't really need them to be injective in general. You can take anything which has zero cohomologies and so on, and so you can work with the fine sheaves which are the Dolbeau, what is called the Dolbeau complex. But in the algebraic context, there is actually, because these are all coherent sheaves, there is actually a natural resolution which is called the Godma resolution, which is also worth looking up if you have not seen it before, and which automatically gives a good Flask resolution of these things, and so you can compute. I mean, the point is then you don't need to do this kind of patching. It is because the complexes are canonical, the maps naturally extend and everything. So this Eilenberg, Karta-Eilenberg thing is for a general machine. Here you don't need to do that. It is automatic. They are not quasi-coherent. But the original guys are, you're saying, yeah, but I think in that it doesn't matter that these are quasi-coherent either.
All this Karta-Eilenberg you can do within
Okay. Right. So this is in general sheaf cohomology, but then general sheaf cohomology is the same as quasi-coherent sheaf cohomology. So, okay. Anyway, so it gives you a way of at least quote unquote defining it without any ambiguity. Okay. Why did I want to say this? Yeah. So having said this, now one can say that one can use this theorem. So which is the theorem which is, in some sense, this is Grothendieck's algebraic de Rham theorem. It's not the way in which it's usually stated, but I will state it like this, that there is a natural map from see the constant sheaf to this in the analytic topology. Or if you want to be very precise, okay, there's no map like this. Okay. There's a natural map in the other direction. Okay, where this star means you allow poles of arbitrary order. Okay, but this is in the algebraic context. This is going to be equal to j lower star because the complement is a divisor, and you know if you put something inside something else where the complement is a divisor, then there are no higher RIs for coherent sheaves. So this is j lower star because it's even in the analytic topology because it's what is called Stein. It's like locally it looks like a punctured disk, as Nitin was saying, or a product of punctured disks, right? And so j lower star x, but this one computes the cohomology of x, and this one therefore if you prove this is a quasi-isomorphism, so that is Grothendieck's algebraic de Rham theorem, then this means that this computes the cohomology of x, not x bar, but already x. Okay, so this guy computes the hypercohomology put here is hypercohomology of this, which is the cohomology of x with C coefficients, of course analytic topology, right? Because here you have analytic, well that's also something with work to be done there. So this actually computes the analytic topology, the cohomology of x in the analytic topology, which is what we wanted. So right, so it's usual cohomology of in the topological sense of x that we want to associate a mixed Schwarz structure on that. Okay, and now we found a way to compute that purely algebraically. That's the main point of the Grothendieck algebraic de Rham theorem. So let me write that here, that H hypercohomology of x bar with values in this complex, right, with coefficients in this complex rather, is H star, H dot, or H star of x C analytic. Okay, so now we have found a candidate where we can try to do some geometry. That's the idea. Okay. So we want to understand what are the filtrations. So that was another reason I wanted to talk about the double complex. So this has a natural filtration which is called sometimes called the beast filtration. Filtration Beth. Beth means beast or Beth means stupid? I don't know. Okay, anyway. So there's a filtration which is you just take the higher order terms. Okay, so you take so-called sigma greater than equal to k of f dot, which is fk. So k I've got k to k plus 1. Okay. Which way is there a map from this complex, between this complex and the original complex? I mean, the diagram of differential has to commute, right? That's all you need for the map of complexes. So if I put f0, fk here, does this diagram commute? It commutes, right? So there is a map from this complex to this complex. Okay. And so there exists a map from h dot sigma greater than equal to k f dot to h dot f dot. Okay. And therefore that gives a filtration. And this decreasing filtration is in fact the same as the filtration coming from the spectral sequence. So using this, you get a spectral sequence by the usual business of spectral sequence or double complex if you calculate it in some direction, which at this point, if I do it, yeah, I suppose you have to take the graded like this, right? And where E1 PQ will be HQ X bar or whatever of FP, okay, converging to, so there's, I mean, whenever I have a double complex, I have a spectral sequence or double complex, which is one of the things which actually is done correctly in Griffiths and Harris, strangely enough, okay, considering the number of mistakes in the book. This one is actually correct. I learned it from there, so I hope it is correct. Otherwise, the rest of my mathematics is wrong. No, there's no signs here, so.
The differentials and whatnot.
No, that's okay. There it's okay, yeah. I hope. Yeah, no, I mean they have chosen signs alternating and so on. So that,
Also interchange P and Q.
no, that is correct here. Okay, so there is such a spectral sequence, and as I said yesterday, a spectral sequence, this spectral sequence means that the infinity term is in fact grade F, grade P, F, H, P plus Q, F dot, where this is this filtration. Okay, so that's the point, that's the relation between that filtration and the spectral sequence and this cohomology. Okay, so that's a general statement always. Okay, so for any sheaf hypercohomology, it has a natural spectral sequence, E1 PQ spectral sequence, which converges to the hypercohomology, and the associated graded are the infinity terms of that spectral sequence, and that spectral sequence, that filtration is coming directly in this sense. Okay, so that's worth knowing. Okay, that's a general statement. Okay, so therefore we got one filtration. This is going to be our Hodge filtration. Okay, so in our case, sigma greater than or equal to k, the image of sigma greater than or equal to k omega dot x bar log d to h dot omega dot x bar log d image. This is, and that we have identified as I wrote here as with the usual cohomology, is equal to fk of h, x and c. Okay, so that where, and this will play the role of will be the Hodge filtration. Okay. And the other thing we want is the weight filtration. So I mentioned yesterday, so let me again say this in terms of this notation here, that the weight filtration Wn of omega dot x bar log d is Ox bar span of things with at most n poles. Of forms.
Excuse me, Kapil.
Yeah.
The filtration was supposed to be on HR. So what is HR?
We'll come to that.
Or ER?
We'll come to that. Right now we are defining it at the level of C. Okay. That takes some little, that's one of the things which I'm getting some 2 pi I is in the wrong place and so on. So, okay. So, span of, yeah, thanks for reminding me. Yeah. So right now we are defining the weight filtration at the level of C, and we'll see. So span of forms with poles on all at most k components. N. Okay. So if you want to be a little more, whatever, more in terms of local coordinates, this means that it looks like alpha wedge b f I1 wedge fi1 wedge b fir by fir, where r is less than or equal to n, and of course I1 etc. IR should be less than k, right? Remember that there were only k of those had actually corresponding to components in, that's where my got confused, okay. So there are at most k components in your neighborhood. In a local neighborhood, remember that's written here. Yeah? So there are, here in this neighborhood, there are k components, I1 up to ik. I rubbed out the top line there. And so that k is here, right? So okay. So this is going to be the weight filtration. So the image of, again, so I suppose it needs to be remarked that it's closed under differentiation. And in fact, you have one more property, which is that omega dot log d times wedge omega m, right? Or w m log d obviously is contained in w n plus n log d. So it's a neat algebraic structure inside. That one is a bit strange, but
so
this one is.
Two obvious questions.
Huh.
You told how the right hand side there is independent of x bar.
Right.
How about f's and w's independent of x bar?
Not like this.
Not like this. Yeah. Yeah. So no. I'll mumble a few words. Okay.
You haven't said what W is on comma.
Yeah.
There's an indexing change.
No, that will come later. Right. So right now there's no change of indexing. Okay. So the remark why W. Okay. Why is
Why
is f independent is also ultimately it all is okay. So if you're not worried about doing everything in terms of coherent sheaf cohomology, you can define everything in terms of this complex which we wrote earlier, J lower star C, which is right. So which is omega x bar star D. Okay. Which is J lower star of omega x dot. And it's relatively obvious that this side doesn't depend on the completion. I mean, you blow up, you'll get more divisors, you'll allow poles on those more divisors of whatever order, it doesn't matter. So in some sense, this one is clearly, if I define everything directly in terms of this, then there's no ambiguity that it is independent of the completion. Okay. Or you can do by, as Srinivas said yesterday, you can take two guys and dominate it and so on. It amounts to the same thing ultimately, I suppose. So one can define the weight filtration in terms of, and the Hodge filtration in terms of this, okay, and which is done in the Leans paper.
What's W0?
W0 means no pole, that is omega x bar.
Correct. HI of that has weight I.
Right.
Zero.
Right.
So that's what I meant about re-indexing.
Okay, let me see.
I plus N or something.
I plus n will be the weight. Yeah.
There's some much more horrible thing in the other case, but that
That's what I was trying to keep track of, but
No, that is your business. I don't remember this too far. So this is easy.
okay. Anyway, right now let's call this Wn. We'll see. We'll see what weight it goes to. So in terms of this guy, this filtration turns out to be the
Kapil, if I can interrupt
Yeah.
for a second. Wn means you're allowing the weights to increase n beyond what would be on a smooth projective line.
So on,
That's the way to do it.
yeah. Anyway, I'll try to explain Wn a little better in
That's why
a short.
W0 don't allow it to change at all. So is that right?
Yeah. Yeah, so I suppose maybe Nitin's point would be it's obvious that W0 is a complex which only depends on x bar and doesn't depend on D at all. So how is it that we are getting back anything to do with x? Where is the D going away? But the point is that of course we are going to take image. Okay, so we are going to take the image of the cohomology. Okay. So anyway, everything can, and in Deline's notes, he has explained both these filtrations in terms of this complex, okay, in terms of principal parts for the Hodge filtration and in terms of truncation for the other filtration. So at this stage, let's first introduce a Hodge structure, then we'll worry about whether it's invariant or the X bar, etc. Okay. Okay, so as I said, so as Srinivas was pointing out, the definition is that Wn plus I of Hi of xcc, whatever, is the image of Wn Hi of Wn of omega dot log. Okay. So at least, we have a definition for whatever it's worth. Okay. So when image F is the Hodge filtration. In this cohomology is the complexified weight filtration. Here anyway we are giving the filtration on the HC. We are not doing it on HR.
Right now, not justified that it's defined by R subspaces.
No. In fact, we have called it that. We haven't even proved that it's a Hodge structure. So the way in which, ultimately the proof of all these facts that it is Hodge structure, etc., comes down to, in some fashion, has to come down to the original two computations, okay? So which is, as I was saying, it is due to Hodge and Kähler. Hodge's computation that for a complete situation, the cohomology is computed by harmonic forms, and then Kähler's extension of that, which is to say that because of certain identities involving, Anant is smiling to say, it's okay. I hope that Kähler is right.
Otherwise would be HIXR, right? Weight filtration is in
That's what Nitin is objecting, but right now we are just giving it at the level of C. Okay, because we are doing everything with complex coefficients because we are working with varieties over complex numbers, but we will have to prove and we'll have to choose everything correctly so that it is actually defined over R. Okay.
But the real structure is obvious from the right hand side. No? After all, the
Cohomology has a real structure.
Even rational.
Even rational or integral cohomology, right? So the cohomology itself has a natural structure. The question is, does this filtration, is it compatible with that? Okay. So ultimately the calculation is going to depend on going to projective varieties, and that is done by the following observation, is to calculate what is grade Wn omega dot x bar log B. Okay. So we want to calculate this in some sense. Okay.
At the level of complexity.
At the level of complexes, yeah. Okay, remember that when you have a filtration and you have a filtered complex, then you have a spectral sequence, and therefore if I can compute these terms and see that they will be appropriately weighted pure Hodge structures, then in fact your ultimately, if your maps are going to be maps of pure Hodge structures there, then everything will be compatible and you will get that the associated graded will be all the weight filtration business will follow. So it's really about showing that in some sense with this, the Hodge filtration gives rise to a Hodge filtration on the cohomology of this as a pure Hodge structure for each I. Okay, so essentially we want to prove that F dot gives a, with appropriately shifted and so on, so gives a pure Hodge structure. On the cohomology of this. Okay, with appropriate weights and with suitable weights. So to do that we have to identify this object. And notice what is happening. So suppose let's take the simplest case. So what is the simplest case? And essentially that's all we really need to understand. So take the simplest case where there is exactly one divisor and that divisor is smooth. Right? So let's take the simple case. D contained in X bar, smooth divisor. Okay, so this now links back to Anand's lecture in the morning in some sense, or maybe Srinivas's lecture yesterday, because everything is going to come down to what happens around D, right? So grade, so there's only one term actually because N, right? So you're kind of interested only in two things if you want to put it that way. So W0, as Nitin and Srinivas already remarked, this is just omega dot X bar, right? Because you're not allowing any poles. So this is just omega dot X bar. So really the interest is what is grade 1 W. And what does it look like? So there is one equation locally for D, and you are writing dx by df by f for that equation. And then other than that you have just an ordinary form and everything is happening mod f in any case. So this is essentially, let me write it within quotes maybe, but then we have to make it formally correct, is omega of dot of D wedge df by f. Okay, except now you have to be very careful because the numbering has to be correct, right? So the dot here, if this was n, this will become n minus 1. So there's a shift of and, right, okay. And now the situation with multiple components is going to be similar, right? So you can do it in various ways. Srinivas pointed out to me that maybe the simplest way is to choose a numbering of the divisors. Let's call them D1, D2, D, whatever, some S is the components. Right? And look at the disjoint union of di, I going from 1 to S, and call this D tilde. Okay, so D tilde is not sitting inside, of course, in the image because it's intersecting. Right? So you have map from D tilde to X. And then I can take fiber product. But I don't want to take the full fiber product because I want to use the certain order which I have. So I want to give each, so after all D1 intersection D2 will come in the fiber product as D1 intersection D2 and also D2 intersection D1. Right? So you have to be a little careful. And so you define D tilde K. So maybe. So disjoint union over I1 less than I K less than or equal to S greater than 1 D I1 intersection D I K. This is, so this I will call I1, I suppose. I is bad. This I is bad. Okay. Too many I's. A. Okay. Is equal to D tilde S. No, K. Sorry. Okay. So note that each of these D tildes, D tilde 1, so D tilde which is D tilde 1, right? D tilde 1 is codimension, I mean dimension is 1 less than x, this is dimension k less than x. Okay. And of course if you want to do everything correctly, maybe D tilde 0 should be x bar. Everything is with x bar, by the way.
That's the assumption.
Okay.
And that D tilde should be D tilde 0. And x bar.
No. D tilde is codimension 1. So I want to keep.
You want to index by codimension.
Index by codimension. Okay, so these are various things, and then you just have to do appropriate checking, and essentially you have to, the analog of this identity will be that grade n or grade k of W omega x bar n log D will be omega n minus k D tilde k wedge, so to speak. So again within quotes, so that's the part which you have to figure out. F I1 F I K. So yeah, so you can see that already I'm making a mess because there should be a direct sum over all those components and so on. So maybe I should put an I here and call this component as, this is, not I, A. Whatever. Right? Call this as A and call this DA tilde K. A indexes the disjoint components of this variety. So D tilde A, K, and then A1. Okay.
Then you want direct sum over all possible capitals.
And then direct sum over all A's, right? And then you have to take I lower star of that. I k lower star.
Each individual term is sitting on x bar.
Yeah.
That's the point of taking direct sum over A.
Right. Each term is sitting in x bar. Yeah. Yeah, but the standard simplification machinery is a bit of a mess to learn. I mean, this yeah, but this is a finite simplicial complex. No, I mean in this case it's a finite simplicial complex.
I don't want to get any questions in the audience.
Well, if you want to be really precise, it is not correct to write this because this intersection may be empty. Okay, so you have to only take the terms where the intersection is non-empty. Otherwise,
Formalism which deals with empty things.
He's ordered the component from D1 to Dn.
Dalin doesn't do that.
Dalin doesn't do it.
I don't like this ordering. It uses the regional schema.
Exactly. So you should read Dalin. He has tensors, everything is an orientation sheet. And that takes care of all of these things. You like that
Yeah, I
You
mean,
need
it should
even
be
a-
automatic. What I'm saying
No,
is
but
all
then
this.
it's not even global normal crossing. It's enough to work with local normal crossing.
That's-
The
that's-
orientation sheet could really be something complicated.
Yeah, because then. Okay. In any case, therefore, so I hope the idea is clear that the associated graded is going to now boil down to computation of omega dot on a smooth variety, which is going to be where we are going to say that you got a Hodge structure. Okay, the only thing is you have to take care of these DFIs and by residue formula or something, and that is where the Gisin kind of construction will be relevant, because you have to unresidue-fy or residue-fy or whatever is the right approach, right? So there's a so the statement is that the residue isomorphism of grade, what did I call it? Grade K, W omega dot x bar log B 2 is isomorphic to omega dot d a k. And there's no log now. N minus, okay. Dot minus k. Direct sum over A. And as I just remarked, you should actually take the direct sum only over components which are actually exist, right? There may be intersections which are empty. So A is such that this is non-empty.
Is empty omega dot to the zero problem?
No, I mean it's just it's not a codimension K variety. That is the
An
issue.
empty codimension K, right?
Well, okay. Anyway,
Yes, exactly.
okay. I'm more comfortable with the K like this. Okay. I'm trying to make it explicit. Exactly. I have this.
Bury it in that notation.
Okay. So anyway, so the thing is, everything is projective, and as Srinivas remarked, if you are taking the direct sum, you can compute the cohomology independently. I mean, you don't have to take the direct image or under. You could also have taken the image of those sheets live here, and then you can take the image, but it doesn't matter. These are all individually they are embeddings. So it all comes down to trying to see that these give Hodge structures, and that is the original Hodge theorem. Okay. The only thing which you need to be careful about, which we have been skipping so far, is what happens to the integer cohomology or the real cohomology. Okay.
Any area creates a torsion, so you cannot talk about integer.
No, but you can talk about integer cohomology. So there is integer cohomology which is sitting, so Zxn, right, which is sitting inside Qxn, sitting inside Rxn, which is sitting inside Cxn. And the universal coefficient theorem says that the cohomology of this guy is the original cohomology tensored by whatever. So H dot of X. So that's not a problem. Okay. I mean, the fact that, and all the other guys in between. So what one wants is to make sure that whatever we are doing, we can keep track of where the integers go. Okay. And so in order to do that, we have to understand this df by f business. Because that could, in some sense, change integers into non-integers, right? And typically, in fact, it does, right? Because dx by x, in order to define the residue map, you don't get 1, but you get 2 pi I. Why do you get 2 pi I? After all, in algebraic geometry, dx by x residue is 1. I mean, where is the 2 pi I in? No, so I want to say that in algebraic geometry, if I take the residue over a field of which may have something to do with complex numbers, may not have to do with complex numbers, the residue is always 1. Okay, but somehow when we do it over complex numbers, suddenly where does the 2 pi I come from? And the answer is, the reason is because you are doing integration. In the usual residue, when you do it in algebraic geometry, there is no integration. But here you are doing integral over a cycle. Okay, and that's where the fact that you are working with simplicial cohomology makes a difference. So usual cohomology makes a difference. The fact that you are working with usual cohomology with integer coefficients, which you are representing by simplicial or whatever, what do you call them, singular complexes, and then you're integrating over the singular chains, you will get the 2 pi I. So that's where that 2 pi I will come here. Okay, and Delin has worked out. So I mean basically there will be a 2 pi I to the power k, 1 over 2 pi I to the power k, or now it should be 2 pi I to the power k or 1 over 2 pi I to the power k is the part where I got confused. But Delin has worked it out, and so I took a walk thinking I'll clear my head.
1 over 2 pi times dx by x is the thing which...
Yeah, so that's all that you have to remember. So that 1 over dx by x, this is what is the ordinary... This is the, so this is the one whose integral is 1, right?
So in Dirac cohomology, this is the integer class. So multiples of this are the integer cohomology inside the complex cohomology.
So not only do you have to do this, but you have to put in that 2 pi I factor, and those 2 pi I to the power k's are kept track of by saying that you are going to twist your cohomology by r, this one, you are going to twist by rp or r minus p, okay, or in this case zp, okay. So 2 pi I to the power minus p z contained in C, or if you want from yesterday's notation r, this is what is called r minus p. Okay, so now you see from yesterday's notation we had r minus p and we wanted a canonical basis of it. That canonical basis is this 1 over 2 pi I which is appearing. Okay, r minus 1 is 1 over 2 pi I. Okay. So that 1 over 2 pi I to the power k comes from here. So your weight is in fact shifted as twisted by this also. Okay. So modulo all this, then it's about, so as I said, so reduce to x is smooth projective. Okay. So the point, again, just to emphasize what is the point. The point is that if you take integer cohomology sitting inside this and you want to get the correct filtration there after doing the grading, you will have to put the 2 pi I factor in order to make sure that your weight filtration is defined over Q or R. Yeah. Okay, so in the smooth projective case, as I said, this is the classical Hodge theorem. So this says that if X is smooth projective over C, then this filtration, the given filtration. So in this case, there is no weight filtration, there is only W0 is given Hodge filtration. Gives a Hodge structure. Okay, so yesterday so those who, I think Delin doesn't give too much detail in his paper about this, but it is generally covered in many places for smooth projective varieties. So there are two parts to this, to the proof of this. One part is the algebraic identities involving these differential operators, the Laplacian with del bar and the Laplacian with d and so on. So there are some identities, and then there is the Hodge's original theorem, which is to prove that when you take the Laplacian when you forms an elliptic operator and therefore various things. That's the analysis part. So there's a kind of purely algebra part and there's a very purely analysis part. Okay, so I'm not going to go into those details. Okay, that gives you a Hodge structure. Okay, so maybe I should just briefly stop and see if there are any questions. I mean, it's been very sketchy, but I hope the basic idea is clear that given a smooth variety, one can associate a natural Hodge structure on its cohomology. Okay. You want some remark?
I'm just thinking, you had that basic example where D was smooth.
Right.
You can write the long exact sequence of pair.
Yeah. Oh, I wanted to remark, if you want to, yeah.
No, nothing. And then
right. So that, yeah, so this was this Srinivas remark that you look at x bar d, right? And then you can talk about for a pair. My remark was something else. My remark was that in some sense, one way to understand how the boundary maps work at the level of integral cohomology directly, you can try to understand, you can replace, suppose it was x bar d is smooth, then you can see that the grade 1, which we wrote down, lives along d. And therefore you can use deformation to the normal cone to reduce it to nx ndx d. And so it's essentially doing everything for that line bundle, and therefore you've got a cohomology on the normal bundle of d in x bar, and which is the same as the cohomology of d itself, except that now we are going to keep track of the Hodge and weight filtrations. Okay, and which will be slightly different, because in one case we are writing a complex for omega complex for n, and in the other case we are writing a omega complex for d. Okay, so you can do it that way, and you can try to see it directly in terms of normal cone, because this grade 1 complex lives on d, therefore you can compute it on the other side. Okay, so since you have learned deformation to normal cone, you could try to do it this way, which I don't know if anybody has written it like that. Elzine does it that way. I see. I see. Okay. But it would be an.
Paper is in French and somewhat sketchy.
Okay.
You said probably as much as
as much as he says. Okay.
a little more in my
Okay. Anyway, I mean, it would be a nice exercise to try to work it out in that sense. That is what I thought would be having done. Yeah. And then one can see that the first gen class being a twist by 2 pi I is what will, see, you're going to take something and you're going to restrict it to the divisor. So therefore, it comes to restricting using first gen class. And so one could see therefore that the first gen class 2 pi I factors play a role in this calculation. Anyway, okay. Sure. Right.
So for the Hodge filtration, you gave that the image of that
Right.
transition.
Right.
For the weight filtration, you gave a filtration at the level of sheaves. How? I mean.
No. Then once you have a filtered complex, you get the image of the filtered. I mean, you do the same thing. The image of the filtered piece is the filtered piece, except here, as Srinivas pointed out, there is a shift in the weight.
Yeah, but you gave this at the level of the sheaf.
Okay, let me write it down and then maybe it will be clear. So omega n wn omega dot x bar log d we defined, right? And I can take its hypercohomology.
So instead of E to PQ, he is giving the.
No, I'm not even going to E to PQ. I'm just saying there is a complex, there is a subcomplex, I mean there's a complex, there's another complex, there's a map of complexes, so there's a map of hypercohomologies.
That's correct, yes.
I mean, what we want is something stronger.
The level of complexity of sheets. It's important the filtration compared with D.
Okay, so you do get a map like this, and then you will say that the image is Wn plus I or something. Okay. Now, there are still some things, I mean, which I am totally skipping. So you have to know something about the fact that in order to apply this to this, you have to know that the associated graded will be in the will map to the associated graded. So some spectral sequence business will show up. I mean, you have to take the spectral sequence of the filtered complex and say that the maps are maps of Hodge structures and so on. So all that will have to be done.
May I ask a completely silly question?
Well, it's never silly.
There's a whole lot of it which was purely algebraic, right? Do it in characteristic.
Okay.
And there was a bit of it which was
That okay, we can forget that.
Forget that. Can you somehow link it with elliptic cohomology? Perhaps 2 pi I.
No, so you can do Dirham cohomology. You can no. So what I think Srinivas has also written up something on this on the Dirham cohomology side, maybe. I don't know. In any case, you can directly do. Right. So there you can do this whole thing instead of doing it with elliptic cohomology. You can do it directly with algebraic Dirham cohomology. Algebraic. So whatever we have done today actually is all works with algebraic Dirham cohomology.
Also link it like here you had topological, there you have elliptic.
No, you don't expect such thing. If you want to do it like that, you have to bring in W omega. You'll have to have Dirham weight.
Yeah, that is one.
This will have only sort of what part of the cohomology. The rest of the stuff will involve other things which you can't just get from covariance cohomology. Not so easy.
And the other part of my silly question was, has 2 pi I and in the putative analogy anything to do with take twist?
Yes,
Yeah.
it is exactly true.
Yeah, because it's exactly the first gen class business.
Take twist is the hot realization. Sorry, 2 pi is the hot realization of take twist. So Kapil was trying to say at an abstract level, he's just saying something like deformation to the normal core and the Chern class in some abstract world, and then when you go concretely to art theory, it suddenly becomes 2 pi there. But he's saying there's an abstract way of talking about weights, etc.
Right? I suppose, okay, maybe. Yeah, I don't know how much to talk about this. So anyway, since you already got carried away a little bit.
If you have material to cover, we should keep track of the time. Sorry.
No, I think today let's do this and then.
No, it's fine. Discussion is also best for this.
So note that you have this map, right? O to O star f goes to e exponential f, right? X is an analytic variety. You have this map, and the kernel is 2 pi I z. Now you might say, why don't I just put the 2 pi I here? And the reason I don't put the 2 pi I here is because then, okay, so
you put the 2 pi I here
instead of there, okay? So the reason is that I have a map from G goes to dg by G. This is a purely algebraic map. So this map is well defined, doesn't involve any whether it's complex numbers, whatever, right? This map is always well defined. And this is exactly the map which will give me the map at H1 level will give me the class in pick. Okay, the first gen class in pick. Except that, as Nitin will point out, you have to be careful about the sign. Okay.
That's not what I was doing. You say you're hiding 2 pi somewhere and it will come out somewhere. It's like exactly those rational MKs in Coulomb's law. They want to hide the 4 pi and then appear somewhere.
No.
So, comparison between Dirham cohomology and
Yeah, the comparison between Dirham cohomology and singular cohomology brings in the 2 pi I. So that's
See,
the way to
if
see
you
it.
write a second sequence below and write vertical maps, the pi will come on the first map.
No, but my point is this map makes sense.
The diagram will come without the pi.
Yeah, but there Before that is a C. C to O to omega 1.
Huh.
Think of this. And you may take omega 1 close so that it's right.
You're saying like this.
Now on the left,
No, but this diagram doesn't commute.
What?
Oh, df by
then
it does commute. Obviously it commutes.
That's coming.
Yeah, it does commute.
But now I'm saying, now look at the curve. And on that map, now you'll have to put a pi.
No, it's just
Meaning-
include.
okay,
no,
include
the
the-
kernel is
but what
R
is
of
this?
C of 1.
Algebraically, the
See,
first
I know.
map doesn't make sense. See, if its head goes into any ring, but what is this?
2 pi z is sitting inside Ox, no?
No,
It's a
there,
number.
if you really want that expression, you have to be much further. You have to go to periodic or theory. Look at the Fontaine ring. 2 pi lives there.
Yeah. And we'll also disambiguate what is I.
One has to do everything with the required level of sophistication.
Yeah.
Otherwise, it's a mystery.
It is.
It is still a bit of a mystery. So
That's one of the hard things. Is that
so the definition, the best
It's like some hierarchy.
the best explanation that I can give at this point is what Srinivas already gave, and which is useful to remember, is that whatever we did today is defined at the level of algebraic de Rham cohomology. So we did not actually, in order to state this theorem, of course, we need to talk about the complex topology. But as such, the definition of the log complex and everything else, as Nitin pointed out, makes sense in any characteristic and whatever, right? You can talk about.
Absolutely, and it's useful and
Okay.
the theorems prove
Okay,
that
and it
compact
works.
and
So, for example, it works with Q coefficients. Suppose you had a variety which is defined over Q, say P1, then it makes sense to do this entire calculation of de Rham cohomology of P1. Okay, and you can write down its class. Now you can ask, what is the Q cohomology? So now you've got two Q vector spaces sitting inside the C vector space of the cohomology of P1. The algebraic de Rham cohomology of P1, and now you want to compare it with the singular cohomology of P1 analytic C. And your factor of 2 pi is going to appear.
Exactly.
Okay, so in other words, there is some theory which is called the theory of periods. Okay, which is about what is the matrix which relates integral cohomology in the singular sense with the coefficient Q cohomology when you think of the algebraic variety which is defined over Q, taken in the de Rham sense. I hope the point is clear.
Okay, my next question.
Wait, let me complete what I'm saying at least. So you've got a variety, let's say x is equal to P1, right? And which is defined over Q.
you can take it x2.
And you can calculate this omega dot of x, no problem. And you can take, as Srinivas says, you can calculate its second hypercohomology. Actually, in this case, you can do it by hand.
Correct.
Okay? And so this is a Q vector space. On the other hand, if I tensor with C, this is also a C vector space, and as we just said, this is equal to the singular cohomology of P1 analytic with Q coefficients, tensor with C. And this is an equality. Okay, so there is an underlying Q vector space here. There are two Q vector spaces inside the same complex vector space. The question is, what is and they are both one-dimensional, so there's essentially just some scalar. Okay, now of course you might object saying that scalar is only determined up to a rational number, which is correct. So the 2 is meaningless in that sense, but it comes up naturally because of the residue. Okay, so then in some sense, if you do it with integer coefficients correctly, you should get exactly 2. But we are doing with rational coefficients, so what we'll get is 2 pi I times a rational number. Non-zero rational number. Okay, so the matrix will be this matrix, and that's where there is period. And this same idea actually is something which exists all through in the theory of algebraic cycles. It's called the periods of algebraic cycles. So it's about relating the cohomology with rational coefficients taken as de Rham cohomology, which can be calculated purely algebraically, and seeing what happens when you integrate those cycles over simplicial chains, singular chains, I think they are called, right? So that will give you the period matrix, right? Because this side is singular chains, is cochains. You want to calculate the cochain. Okay, so the 2 pi I is coming from there. I mean, it's useful to know that that's how it comes. So, okay. So the I you can't get rid of, the pi you can't get rid of, but the 2 in some sense is convention.
When you are swapping it over Q.
With your sloppy
We must also the integer.
Right.
The Dirac Mohali has a natural integer structure. So up to sign, it must be okay.
Well, and the sign is fixed by the fact that something has to be a positive line bundle.
If it has section.
I think that fixes it. Dalin does say something about the sign in his notes, and he's careful about it. But there, at least when I read the paper, which is a long time ago, so I've forgotten, there's also the convention of what is the sign you take when you take a boundary map in.
Exactly. That pitfalls.
So
whether you shift the complex and then take it, Dalin gives a paragraph or two.
2 on this. So you're on the problem is that in homological algebra there are lots of conventions, and you have to fix your convention, and then somebody else's convention will be different, and then you have to see whether your convention, how does it go to the other person's convention, and so on. So basically it's a mess. So it's easier to fix things after the fact by saying things like, if it's a positive line bundle, then it has sections. And we know what is the sign.
No, but to go from there to Mohali, you made some choices. And there you could have introduced more signs.
Right.
This is actually one of the principles you think you can calculate.
Right.
It does partly.
Yeah. But by the way, Nitin pointed out to me, and if any of you are reading Griffiths-Harris, you should be aware that in Griffiths-Harris, the way they define signs for the first gen class, turns out that all positive line bundles are negative according to them. So they have actually made an error of sign.
There's a paper, I think if I remember right, of Attia and Hitchcock, which has an appendix about the 8 different definitions of the first gen class in the literature. And the comparison marks between the...
Where is this paper?
I think it's Attia and Hitchcock.
It's the same paper, I think. Okay, so today I think
Another question. Suppose you have over big vectors or something like that, and you are and you can do your algebraic theory at the close point, at the generic point.
this has become a discussion session, but okay, I think that's
And
okay.
you also have your topological theory over your generic point and the analytic theory over the close point. So how does this compare? Algebraic theory varies nicely based on what you are doing.
I'm not.
Weights are supposed to vary.
Weights are supposed to.
Meaning it's
If we assume the standard conjectures, probably they do.
So therefore, does it help you show there is no this?
That's the question we can talk about.
Okay, maybe we are getting really. So I hope the basic principles behind how we are introducing mixed order structure on cohomology is clear. Okay, and so now everything for the next lecture I will only talk about this case. This case. Okay. So I didn't want to start on that, so I'm going to spend some time on talking about the case of pure Hodge structures and smooth projective varieties. There's some question?
So this is a pure Hodge structure.
This is a pure Hodge structure of weight n, so maybe I should have said this. So X is a smooth projective variety, and then Hn of X analytic C, okay, with Q coefficients or R coefficients carries a pure Hodge structure.
Exactly what we know about complex scalar manifest.
Yeah, I mean, in fact, can replace this with compact Kähler. Okay.
Birationally Kähler is one. So if you have smooth proper varieties of C.
Okay. Okay. Or you could have blown up a Kähler variety. Yeah. Okay.
Same as the Hodge structure you defined, right? This usual Hodge structure we know by in
Yeah, I mean, the degeneration, etc. So I didn't quite get your question.
I mean, we know a Hall structure coming from these harmonic forms and all.
That's right.
And
That is, all that has been used in some sense in order to prove everything, because finally we reduced to this case. Okay, in the general case, what we did is that we gave filtration, and the associated graded were sitting inside these as kernels of maps of Hodge structures, because I rubbed it out somewhere. So there was a map of cohomologies, which is a map of Hodge structures, and therefore the kernels and co-kernels are Hodge structures. And since they are pure Hodge structures, the kernel and co-kernel are pure Hodge structures. So the associated graded of your weight filtration are actually pure Hodge structures, which is what you need to prove in order to prove that what I have is a mixed Hodge structure. So I think, let me say it again. So first of all, you start with a variety, smooth variety. You put it inside a smooth projective variety. You take the completion, right, with divisor with normal crossings, and then in the way in which I described earlier, you get two filtrations on this. Okay, one is the Hodge filtration, one is the weight filtration, and then you compute the associated graded with respect to the weight filtration, and you show that computation reduced to the smooth case by taking those d tildes. Okay, now you have cohomology of those things. There will be a spectral sequence from those cohomologies to the original cohomology. That means the original cohomology has a filtration. The associated graded are subquotients of this. And since the maps are maps of varieties, smooth projective varieties, that we'll see next time again in some detail, that how do we see that. So a map of smooth projective varieties will be an underlying map of pure Hodge structures. And therefore the kernels and co-kernels will be themselves pure Hodge structures. So that means the associated graded of the filtration, weight filtration we started with, is a pure Hodge structure, but that is essentially the definition of what it means to have a mixed Hodge structure. That there's a weight filtration such that the associated graded is a pure Hodge structure. I hope that answers your question. I don't know, right? I mean, the only ambiguity could have been, is it defined over R? And that is what we have been discussing for the last 10 minutes, or 15 minutes, is how do you tweak things so that everything is defined over R. Okay.
I misremembered the quote fact. It wasn't 8, it was 7. This is a paper of Borel and Sextabrook, Characteristic Classes and Homogeneous Spaces, Part 2. 29.3 section says the definitions of Chern classes. And he says, let ICJ be the Chern class CJ according to the I definition. And he says,
I hope this paper has no mistake. I hope this paper has no mistake after that.
well, Borel and Sextabrook. I'll give you, no, it's not Rakia. I keep remembering Rakia or something. It's called Characteristic Classes and Homogeneous Spaces 2. It appeared in American Journal of Mathematics, 1959.
Okay.
Because Mark Levine writing some paper exactly wrestling with these stupid signs and these 2 pi a's and getting into real trouble.
Yeah, so at least in the paper of Dalin, he has correctly fixed his one convention for signs which works.
Yeah,
for
it's
him.
self-consistent.
He's self-consistent at least. Sorry? But I hope this remark is kind of useful to keep track of, that 2 pi is not something mysterious, and therefore pi is called a period. And in the theory of cycles, you will see a lot of discussion about periods, because ultimately whether the periods are irrational or not, like proving pi is irrational or pi is transcendental, is a serious issue in general. I mean, it's every time you prove that a certain period is irrational or transcendental, you have a theorem. Okay, it's not, and the interest is in periods, not in other numbers to that extent. I mean, many people are interested in, those who are doing transcendental number theory may be interested in other numbers being transcendental. But transcendentality of periods is of interest to algebraic geometers.
So Riemann started it with this period matrix.
Yeah, that would be the first example. Okay, so I'll stop early today because I didn't. So pure Hodge, next time pure Hodge structures for smooth predictive varieties, and what is the Hodge conjecture?